Dear students, we will start the second unit in the course Power Semiconductor Drives. First, we will discuss on review of torque speed characteristics of various DC motors like shunt, series, and separately excited motors, and solve some numerical problems related to torque speed characteristics. So we have seen in the previous class the last topic of unit 1, steady state stability of an electric drive. We were able to determine the stability of a system based on the speed versus motor and load torque characteristics. That is speed torque characteristics of motor and speed torque characteristics of motor and load we are considered, and based on that, if there are any disturbance included in the system at equilibrium point, whether the drive is capable of regaining its original stable point or not, that we have analyzed, and based on that, steady state stability of an electric drive was decided. Now coming to the second unit, in this unit we will discuss on the steady state speed torque relations of DC motors. Okay. Then we'll see methods of speed control of DC motors, then starting and braking and the dynamics of DC motors, motoring, dynamic braking, regenerative braking. So that means steady state operations, then speed control, then transient and dynamic operations, and motoring, braking, and regenerative braking. Plus, we will see that how a DC drive can efficiently be controlled with its speed and torque based on the power electronic converters by using the controlled rectifiers and the dual converters and choppers. Today, we'll start with the unit topic on review of torque speed characteristics. We'll first discuss what are the various types of DC motors, their characteristics, and based on this, we can come to an idea that which DC motor is suitable for a particular application. So at the end of the class, you should be able to determine the speed and armature current of DC motors for new values of voltage or field current. So in the problem, the normal or rated values will be given. If there is any change in voltage or field current, then what is the new value of speed and armature current of a DC motor, that you should be able to determine. Yeah. So coming to this, what are DC drives? So DC drives are the one where in an electrical drive system, DC motors are used. So if an electric drive consists of a DC motor, then the drive is called as a DC drive. So these DC drives are finding large applications as compared to AC motors. This is because they are having the capability of adjustable speed. You can adjust the speed. That means you can control the speed to any required value. Good speed regulation. The speed regulation is very fine as compared to AC drives. Then DC drives are suitable whenever the application has frequent starting, braking, and reversing operations. So if there is a frequent transient or dynamic operations existing in the drive, then DC motors are best suitable, and hence DC drives find applications for such critical conditions. Some important applications are still now the industries use DC drives in cases like rolling mills, paper mills, mine winders, excavators, then machine tools, traction. So large power applications, still they are finding DC power or run motors. In this session, we'll describe on the steady state speed torque relations of DC motors. Based on this, we will be able to solve some numerical problems. So when you come to the motors, what are the different types of motors that are there, which you have studied in the previous semester? Separately excited DC motor, shunt DC motor, series DC motor, then compound DC motor. In this you have two types, cumulatively compound and differentially compound. But cumulatively compound DC motors are best suitable for industrial applications. So these will be considered for our discussion. And you can see here that these names of the DC motors is based on the interconnection of the armature winding and the field winding. In case of a separately excited DC motor, field winding is connected to a external or a separate DC voltage, and hence the field current is independent of the armature current. In case of shunt motor, the field winding is connected in parallel or in shunt with the armature winding and then connected to the same supply. In case of DC series motor, the field winding is connected in series with the armature winding, and in compound motor, there will be both shunt field winding and also series field winding. So here it is shown here the cumulatively compound and particularly long shunt cumulatively compound motor is shown. So the steady state relations, if you see, what are the equations that guide for the speed control or torque control of a DC motor, that we'll see. So in general, yeah, for any type of motor, an armature is connected to a DC voltage, and there can be an external resistance connected between the armature and the supply to limit the current. So we have, let us say, this is RA, which indicates the total resistance of the external resistance and also the armature resistance. Then in that case, we can write KVL equation to this as V is equal to E plus IA into RA. So this equation will get V is equal to E plus IA into RA. This E, or we can write it as EB, the back EMF. Back EMF is given by what? Phi Z n by 60 into P by A. Okay, this is given. So you can see that this back EMF is proportional to flux and speed. The other parameters Z, P, A, 60 are constants. So EB is proportional to flux and speed, or you can say that EB is proportional to flux and motor speed in radians per second omega m. So therefore EB will be equal to KE phi into omega m. Okay, so that means we get this equation. This is the back EMF. So applied voltage V is EB plus IARA, and back EMF is KE times phi into omega m. EB is proportional to flux and speed of the motor. Then coming to the torque equation, we have torque developed in the armature T or TA is equal to phi Z IA into P by A. So what is the observation we can make here? That this torque is proportional to flux and current, the other parameters remaining constant. So therefore, we can write this as T is equal to KE phi into IA. T is equal to this one. T is equal to KE phi into IA. So therefore, we can get the relation between the back EMF, flux and speed, torque, flux and current. Then omega m, how does speed and torque relate? So for that, we can make use of this equation. From this second equation, we get EB is equal to V minus IARA, and EB is nothing but what? KE phi into omega m. So solving for omega, you will get V divided by KE phi minus RA divided by KE phi into IA. And we know that this IA can be replaced from the third equation as what? P divided by KE into phi. So with that, you will get omega m is equal to V divided by KE phi minus RA by KE phi whole square into T. So this is important. Yeah. So now those basic equations can be now applied to individual motors and analysis can be performed. For example, separately and shunt motors, they I am considering combinedly because in this case flux is almost constant and hence we can see here. For example, separately excited motor, field winding is supplied with a constant DC voltage. So therefore, IF is constant, flux is constant. In case of shunt motor, applied voltage is normally constant and hence the field current IF is constant, flux is constant. So in case of separately excited motors or shunt motors, the field voltage or the supply voltage is maintained constant and hence flux is practically constant as the torque changes. So even though the torque change, flux is remaining constant. So in the previous equation, we had this KE constant, now I can replace like this k into phi. If flux is constant, this one, if flux is constant, k into phi is also constant. So this I can replace it by k. Okay. So now if k into phi is equal to k, then t will become k into ia. Previously we had t is equal to ke phi into ia. Now this becomes k. So t is k into ia. And similarly back EMF, what we had, back EMF is equal to ke phi into omega m, and now this becomes k. So k into omega m. So now we get these two relations for what? For this separately excited motor and shunt motors. Then omega m will now become v by k minus ra by k into ia, or that is equal to, that means omega m is equal to v by k minus ra by k square into t. Yeah. So now let us see in case of series motor, or in other words, we can make observation here. So what is the speed and torque dependent, that we can analyze from the torque speed characteristics of the motor. So now this is the speed, let us say omega m, and this is the torque. So this torque is in per unit, and omega m is also in per unit. So now under no load condition, torque is zero, and hence there will be speed of the motor, which is called as the no load speed. So this point is nothing but omega m naught. And when the motor is running at rated speed, now motor develops rated torque 1 pu. At this point, what is the one that is there? This voltage, this speed is omega m, or rated speed. You can see this, that under no load to full load condition, the change in speed is very small. Why? Because of this characteristic. How is this characteristic has come? From this equation. For different values of torque, if you plot the omega m points, you will get like this. See, the supply voltage v by k is constant, and here re is very small, and hence this drop is becomes very small. So therefore, the slope is very less, and the separately excited or shunt motor will have the characteristics with almost constant speed. The drop in the speed is very small from no load to full load. So DC motors are suitable for constant speed applications. That's what it gives the information. Now coming to the next, series motors. So in case of series motor, flux changes because the flux changes because the field winding is connected in series with the armature. So as the load connected to the motor changes, as the load connected to the motor changes, then what happens? The armature current will change, and due to this, the field current will also change. Armature current and field current are same for series motor. So as they change, the flux will also change. So that is what is happening here. So now flux is assumed to be proportional to Ia. As Ia increases, flux is also changing. So in this case, for series motor, flux is proportional to Ia, or flux is equal to Kf into Ia. Now your torque becomes what? T is equal to what? Torque equation. T is equal to Ke phi into Ia. Now it becomes Ke kf ia square. Kf ia square. That is what this one. So similarly, speed will now become what? V by square root of ke into kf into 1 by root t minus ra divided by ke kf. So what is the observation here? Omega m is almost inversely proportional to square root of t. So with that, the curve will get like this. Okay, for series motor, for a series motor, and hence at rated torque, you can see this is the rated speed under no load condition. See, when t equal to 0, when t is equal to 0, omega becomes infinite. So there will be large value of series motor speed is infinite, and hence it is not suggestible to operate the motor under no load condition. So series motor should be started with at least some load, and it can give high torque. Why? Because torque is proportional to Ia square. This is the observation. Torque is proportional to Ia square. Okay. Now coming to the compound motor, particularly the cumulatively compound motor. So here the connection of the series and shunt field winding is made such that the series motor operates with finite speed even under no load condition and maintains the speed or characteristics of the shunt motor. So the characteristics of compound motor is in between the series and shunt motors. So you can see here by adding the series winding and also shunt winding in cumulative one, so we can have the torque speed characteristics like this. So even under no load condition, there is no load speed omega m naught, and under full load condition, if you see, this is the rated speed under rated loading condition omega mr. There is change more than the shunt motor, but very much less than the series motor. So that's how the combination of series and shunt motor helps. Yeah. So in general, if you see, there are these four types of motors that are normally used in the drives, and these are the connections. And we can see here torque speed characteristics of the motor of all the motors are shown in one graph. And you can see cumulatively compounded motor, its characteristics is in between the series motor and the shunt motor. Yeah, let us see some examples. A DC separately excited DC motor is running at 800 rpm, driving a load whose torque is constant. Motor armature current is 500 amperes. Armature resistance drop and rotational losses are negligible. So it means resistances RA, RF, all the things you can neglect it. With that, EB becomes equal to V. Okay. Magnetic circuit can be assumed to be linear, so non-saturated. Calculate what motor speed and armature current if terminal voltage is reduced to 50% and field current is reduced to 80%. So what is the change in speed and current happens if we change voltage and field current? So let us see what will happen. Yeah, so these are the values given. Under normal operating conditions, IA1 is 500 amperes, speed is 800 rpm, and resistance is neglected. Then it is observed, it is done with 50% voltage and 80% field current. With that, what happens? In the second case, phi2 will become 0.8 into phi f1. So torque is remaining constant. T2 is equal to T1. So we have KE phi2 IA2 should be equal to KE phi1 IA1, and therefore you get IA2 is equal to 625 amperes. All the values are known. You can substitute and you will get IA2 as 625 amperes. Okay. Now, in for the second case, when the flux is changed, so what is that we can see? What is asked? You have to find the speed. So to find the speed, we can use the back EMF speed relation. So we have E1 is proportional to phi1 into N1 and E2 is proportional to phi2 into N2. So E1 by E2 is equal to phi1 N1 by phi2 N2, and substituting you will get the N2 as 500 rpm. So what is the observation here? Under a normal condition, 800 rpm was there. As voltage was decreased, speed has decreased. As flux is decreased, then the current to maintain same torque, current has increased. That is the observation. Okay? Yeah. So dear students, we have come to the end of the session. So today we have discussed what are the different types of DC motors that are used in DC drives and their torque speed characteristics, considering the basic equations. And we have seen how to solve a problem to understand the effect of voltage and the field current uh, on the speed and armature current. So by now we can solve similar problems like that, and you should be able to determine the speed and armature current of DC motor for new values of voltage or field current. So please try to answer this. A DC motor is selected for driving a load having a large torque for short duration by a long no load period. Which DC motor will you suggest for such application? That is what is the question. Similarly, explain why a DC series motor is more suited to deal with the torque overloads than other DC motors. So whenever there is a requirement of torque under overload condition, we prefer DC series motor. For example, large load applications like traction, lift, escalator, crane, excavators. we try to prefer DC series motor rather than the shunt or cumulatively compound or separately. Why is that? Try to analyze this and we'll discuss in class. So, dear students, please refer GK Dubey textbook and sections 5.1, 1.1, and 1.2. And you can also refer to the solved problems. And there is a much good exercise set of problems given from 5.1 to 5.8. You please try to answer all these so that you can understand the characteristics, torque speed characteristics of the DC motors. Thank you, students.